Okay, yeah. So let's kick this off. So before we go into the guide, I want to share what's going on just in the broader space of GPU versus CPU. And so at the beginning of the year, I just did a quick calculation of like what's the last 10 years of the kind of the cost effectiveness of GPU computing. So on the left, we have just in terms of the amount of compute, the floating point operations per second. And so this is like, like more compute per second, the better. And so what we're seeing is for kind of like over the last 10 years or so, it's been about a 30x increase for like on Amazon, like when you can launch their first GPU instances 10 years ago. For that same dollar, you can get about 30 times more over the last 10 years. I don't know if like anybody's been, a lot of folks have been buying computers over the last 10 years. They have not, on the CPU world, they have not improved 30x. Like I'm running on a MacBook from 5 years ago and or 3 or 4 years ago, and it is, if I buy a new one, it's not 30 times faster. So that's pretty cool. What actually ends up really important in the GPU world is how much RAM you have right on that GPU chip. So like, it doesn't matter if we have so many like cores, because if they're starved for memory, that means they don't actually have anything to do. And so what's kind of cool here on this same chart is for that same dollar, like how many gigs of RAM do we get? And what we're basically seeing is we went from that 1.4 to 30 to about 31. So this is again like about 20-30x increase over the last 10 years for cloud GPUs. So that same dollar, again, we're not seeing that same thing for CPU RAM. So while Moore's law is indeed dead in the CPU world, it's still alive and kicking here. And so, and kind of what that tells us as folks trying to do, Hadoop, Spark, that kind of workload, eventually the GPU stuff just is more compelling. And for the folks who from the RAPIDS ecosystem who are tuning in today, I actually want to say big congratulations. Where I think about two weeks ago you went public, where for the first time a GPU stack officially beat the Hadoop ecosystem on kind of the like one of the main database benchmarks, the TPC BB benchmarks. So and I think it was actually by a wide margin, anywhere like different workloads from 20x to even like 400x. So and that's kind of what's going on with this chart. And because it's in Amazon, Google, Azure, anyone can do this stuff now. So, well, what is RAPIDS? I keep using that phrase. So some folks already know it, some don't. What's going on here is basically we have all those like CPU in memory stuff like pandas, Spark, SQL, Dask, NumPy. Those are a lot of the core building blocks. And then when you're actually getting into application work, we might have stuff on top. You might have machine learning libraries in Scikit. Graphistry, we do a lot of graph analytics. So folks might have been using something like NetworkX. We also do a lot of visualization. So you might have been using something like Plotly or Bokeh or Gephi. Those are actually like, a lot of those were built for convenience. And so they had kind of nice APIs or nice-ish APIs. They did try to do some performance, but a lot of the winners ended up being actually about usability. What's cool with the RAPIDS ecosystem is one of the decisions through a lot of the projects has been just maintaining API compatibility with the CPU stuff. So if you knew pandas for Python pandas, you actually know a good chunk of the cuDF library. If you knew SQL because you're doing Spark SQL, congratulations, you now know GPU SQL, or like you're 80% there. So that's going to be a lot of today. I'll skip this bit on the graphs. Like a Graphistry, we do think about a lot about, if you have a lot of rows or columns in your data, like how do you see the correlations? And that ends up being a lot of graph analytics. So, but you'll see that in examples. So today, for this first portion, what I want to go, I'm going to go through 3 examples. Again, they're all on GitHub. First one, we're going to be doing a bunch of SQL. Doing GPU SQL, we're going to load in more memory than a GPU has, so that'll be pretty fun. And then we're going to go all the way from looking at logs in SQL to actually visualizing them. After that, the second one, we're going to do something similar, but then we're going to do, when we're going to be looking at those records, in that case, we're going to be looking at domain records. We're going to do 2 different things. One is we're going to throw a whole battery of graph analytics at them and see how many we could do quickly. And then the second thing we're going to do, and this still like, I'm personally coming from the academic land, like where I remember writing research papers about this stuff 10 years ago. We're actually going to write regex and have that run on the GPU, and it's going to be no big deal. And then we'll visualize the result. And then for the last one, we're going to touch a bit more on the machine learning side. And so we're going to show an example where if you have a bunch of event records, in this case, we're going to be doing some COVID misinformation stuff. If you have a bunch of event records, we're going to show how to just automatically find the patterns in it and then plot them out and do end-to-end GPU. So this should be a pretty fun one. And then a reminder, this is cool. Take a 20-minute breather and then come back, and then you'll actually do a hands-on for the lab portion. So all right, so let's kick it off. And then as we go along, you know, this is like a new era, new medium. It's kind of cool that we can do this as like an interactive chat. So if you have any questions as we're going along or anything like that, just chat in the Slack or in the YouTube. Okay. So let's kick it off with the log analysis. So this is going to be all in the GitHub. This is tutorial 1. And the technologies we're going to use for this one is primarily going to be BlazingSQL for the analytics. And then we're going to dump it into Graphistry first we're going to dump it into the Jupyter notebook to see the result. And then second, we're going to, from the notebook, drop it into Graphistry to actually see it as a pretty picture and see what's going on. And all this stuff you can actually do free. So we'll take it through you in the lab. But if you're not joining, then go to app.blazingsql.com. You can get you get a free GPU notebook session here that's already set up for the RAPIDS environment. Go to learnrapids.com to find our GitHub to get the tutorial. And then for Graphistry, the visualization stuff, if you go to our homepage here, Get Started, we launched this thing called Graphistry Hub, where you can just get a free online account and play with data. Okay, so for the first one, this data set is pretty fun. So what we're going to be looking at is about 53 gigabytes of logs. So this is something that normally, like, I'd feel a little nervous about opening in Excel or even actually in Jupyter with pandas. So this is like a real amount of data. It's like 53 gigabytes. It's actually, I think it might even be more than the CPU RAM on the box we're on. I actually have no idea. The GPU we're going to be running on is actually, again, I think it's probably 10 to 16 gigabytes of GPU RAM on the box we're running on. So this doesn't even fit in the GPU. So this is a really fun example for the analysis. So, and also, so as we kick it off, one of the kind of really interesting things here, all that data is actually already split between, looks like, man, I don't know, 50, 100 files here, 58 files. And so the first thing when we start BlazingSQL, it's actually not a database. Think of it similar to like starting a Pandas session. Like it's just like this, it's just like this in-memory ephemeral thing. And so we just say, hey, we want to start kind of like one of these scripty SQL sessions. Here's where all 58 files are. We just pass them in, just the URL. They all have to have the same format to be considered part of that same table. We're going to give it the name logs, and then bam, I have 4 seconds later, I've got a table of 53 gigabytes of logs that's now GPU accessible. Keep in mind, it hasn't actually moved to the GPU. Right now, it's just still sitting in S3 buckets. And it's going to be BlazingSQL's job to kind of move data in and out of the GPU memory as we go along. Actually, here's where we actually officially, I guess what was going on here is I also wanted to just do a subset of 10 million. Like, that's still a lot of data for somebody like Pandas, but like for our stuff, it's a nice way to, I often like to have like maybe 100,000 or a million subset just to play with before I do like, you know, the billion, whatever scale. So if you know SQL, you know BlazingSQL. It's actually more about making sure performance works out or that you're in the right, like the subset that they currently support. And so, for example, if I just want to ask how many IP addresses are in my logs, I could just count normal SQL. And we saw in this case, wow, okay, we have about, this is actually about 50, 60 million rows. So they're just counting the number of rows. I could have done the same thing as distinct count and asked how many unique IPs, and that's it. Likewise, if I could just select star, I can see everything. So the data set we're doing today is pretty typical of network and security analytics, where we're using something called Zeek, used to be called Bro, but it's basically a bunch of different types of network connection logs. And so we can see all sorts of stuff about like HTTP and SSH and things like that. So if you haven't seen it before, check it out. It's pretty fun. A lot of, like, in the beginning of the tutorial, it's basically stuff that you'd expect. Like, can you sort? Can you tick, like, let's say I just wanted to see SSH activity. Could I just filter by, port 22? And it's not so bad. And you're seeing here, it's all running through. What I wanted to actually share was this big query here, where whether I'm in Spark or Splunk or BlazingSQL or a lot of other network analysis, but I found that a lot of my queries end up looking like a variant of the one I'm about to show. And so for me, this is one of those. If I could do this query, I could basically do a lot of the analytics on whatever stack I'm on. And so what's going on with this one, the meat of it is really right here. First is, if we're looking at a bunch of like computers or whatever talking to each other, we're going to just want to first group by the source and dest IP. Sometimes I might also do something like source port, something like that as well. And then now I have basically, I can now start asking questions about, hey, when this computer or this application talked to that application, or this user connected to that user, tell me some information about it. So if I'm doing for network performance, I might ask about packet loss or like the sum of packets going through. If I'm doing in a security context, I might ask about like, hey, was there any activity? What was this? How much data came in, come out, like for exfiltration? I might ask like, how many distinct ports? Could I do a distinct count of the number of ports to see, what was actually going on, stuff like that. And so this is just kind of an example of that. And then we kind of ran it through. And you can do all sorts of variants. Yeah, so here you see that I went on and did a case where I was curious about, let's just split it based on all the application ports, like the low ports, things like that. I see actually somebody here is asking about how do the queries compare to something like Spark. I don't know if we have anybody from the BlazingSQL team here who might give like a more like official answer. The way that I think about it is generally maybe if you think about per dollar, maybe like a 10x. The issue there's kind of like different axes of it. So the first thing is like for the same dollar, like you can pick how many GPUs you run. So BlazingSQL, you could do like one GPU, multiple GPU. But basically, when you lock the the amount of energy or the amount of dollar you're paying, that means you get a certain amount of compute, you get a certain amount of RAM, things like that. And so then generally, as long as you can keep it all in memory, the intuition is Spark has to move data and shuffle data between computers. Rapids, generally, if you've got a bunch of GPUs on the same box together, you don't need to pay that data movement cost. It's going to come in and stay in on that same node. So not only do you get the GPU speed up, but you actually skip all that data movement. And actually, a good example of where I want to share using that is, for example, for that one, I just ran right ahead a query to do that same shape of let me see all the port like computer-computer communications, but I filtered that down to just the SSH activity. I wanted to see for this network what that looked like. When we got that table back, and this is where something like Rapids starts looking different from something like Spark. Remember, all of this is running on I'm running on the notebook on a box with a bunch of GPUs. Actually, I think just one GPU on this one. So when I'm working in that notebook, I'm actually looking at the GPU and how much memory is there. And so in this case, when I get that, when BlazingSQL gives me back all that SSH activity and the summary of it, that's actually a pointer to GPU memory. And so when I jump to Graphistry, if I actually had this box configured a bit better, and I said, hey, Graphistry, plot that table, if I had Graphistry running on the same GPU box, I wouldn't have to upload the data anywhere. And so like it's just, even ignoring GPUs, like you just don't pay all that data movement cost that you do with the Spark world and the NoSQL world. So in this case, let's take a look. We're actually running Graphistry elsewhere. Another cool thing about the RAPIDS ecosystem is very early on, I made the call to rally around a technology called Apache Arrow, and it was kind of co-designed in parallel with RAPIDS to make sure it could kind of do the GPU stuff. And so basically in this case, when we take our data frame of all the SQL results, just think of all those different columns, it's actually binary data. And so we're going to move that binary data to Graphistry. We hit .plot, that moves it as binary data rather than JSON or CSV. And that means on the Graphistry side, when I load that in, it actually goes straight to the GPU. We don't really have to do like parsing and stuff like that. We did some validation and stuff, but we're actually able to do all of that on GPU. And so generally, when this case, like we actually have a small network, it looks like a network of results, but you'll be seeing later when we get like, let's say 100,000 or a million results back, it actually, all that data transfer time, even across computers, is actually pretty fast because it's all binary data and it's just memory copied straight to the GPU. So there have been really cool numbers about that. But one local benchmark we had was like, same network, maybe like 100 million things in about a second or two. So yeah, so in this case, what we got is the summary of all that, the Zeek network data. So when we got that, the BlazingSQL result, we're seeing all those byte sums. You know, I can ask like, hey, what was the biggest byte transfer look like? Let's see if we can see which edge that was. Zoom out a bit. Yeah, it looks like so over here we had some some chunk of network had some pretty heavy activity. Whoop. I think my poor little laptop is getting a little overwhelmed here. But yeah, so what we're seeing is one of these links here was super heavy, and we're seeing that around that link, we actually see there's actually another computer that seems to be part of that cluster. And so we can kind of look at these 4 different flows and try to, we might want to piece together what's going on. And so this ends up being a nice, hopefully you're getting a feel for the full ecosystem here. So this ends up being pretty cool. Okay. So let's jump to the next one here. So this was a quick analysis that popped out of the COVID threat intelligence project, where a bunch of cybersecurity analysts have been pulling together threat intelligence around a bunch of COVID attacks. It ends up being a lot of phishing, spam. There's some targeted attacks. A lot of it's a lot of fraudulent domain names, like, for example, people selling fake protective equipment, things like that. There's just like a lot of badness happening. And so Alien Vaults, Sophos, a bunch of good companies help with that. And so here what we're going to do is, given all the new COVID domains that got registered and were getting shared over email, online, places like that, we had the passive DNS data of when they got registered. And so this could feed into various kinds of analytics and investigations of, you know, what's going on. Are these domains good or bad? The reason I wanted to go through this example here was, again, given a bunch of all these like log records, I wanted to show kind of 2 things. The first one is doing regex and running regex on a GPU. And then the second thing I wanted to show was then doing graph analytics just straight in the notebook and kind of working on, given all that event data, seeing what correlations and kind of scores and things we could do. So the first thing did, and maybe the kind of the pause point here is, in a lot of big data, machine learning, data science, whatever, the reality is like 80% of our time is like just loading in data and then wrangling it. And so being able to do GPU regex over like 50 gigabytes of data is actually an important thing, right? And so in this case, for example, the data format we got it in was, we got a bunch of IPs. We had to, what we want to check is something an IP? And if so, maybe we can want to change the format to something faster. And you know, things like that. And so here, and we just did a quick simple regex. This is like an IPv4 where there are 4 dots in it, like there's 4 numbers with dots in it. And if that's the case, like that's just the standard regex here. We just take that column of whether it's the domain name and then whatever the DNS record responds with. If it responds with an IP versus domain, then we'll get an answer, is the query or domain an IP? And the amazing thing about this is like it's boring. That like this is basically, if I was writing pandas, this is what it would look like. I would have taken my table of IPs. Oh, actually, I do want to make a note. Like when I read in the CSV here, we're actually not using BlazingSQL anymore. Now we're just using raw cuDF. So cuDF is kind of how Python pandas is sort of the Swiss Army knife of working with tables in Python. cuDF is the GPU implementation, essentially, of pandas. And so you just load in the CSV, whatever size it is. In this case, we just loaded in 300,000 records. It just loaded in. You don't worry about it. And then now we could do fun stuff like, okay, on the column of queries and answers, could we do the regex? And it just works. Like it's exciting how underwhelming this is. Like 2 years ago, you can do this. Okay, so now that we have that, we can actually start asking questions about, like, basically, if you think about, for example, how Google works, the early versions of Google, they have this notion of PageRank where you can ask like, hey, which page is the most important? So if you have a search result, which are the important ones, things like that. And there's like a really fun wide world of graph analytics algorithms. We're actually gonna probably maybe sometime late August, we're thinking about doing a second session, just like, well, I'll just come back and talk a lot about graph stuff. But the fun thing here is we're just gonna basically run all of them. And one of the fun things with GPUs is if it's fast enough, you don't need to really worry and stress about exactly what you're doing. You can just iterate. And so in this case, we're going to use cuGraph, which is essentially the GPU accelerated version of NetworkX, which is a Python graph library, except for now you can deal with 1 billion nodes and edges on the same GPU. And all we're going to do is take that table of domains and whatever the DNS record maps to. We're going to take that result and then turn it into a cuGraph object. So we're going to change it from one GPU representation to another, that's just something whatever cuGraph kind of likes. And then once we've done that, and you can, I guess we didn't have the timing information, but this is fast. So let me just actually run it live. So we're gonna load in the CSV file, 300 milliseconds. We're gonna run the GPU regex, less than 100 milliseconds. I don't even know what this one's doing. I think we're just doing some pretty printing here, so that was probably less interesting. Oh, actually, we're actually here. This is a good example. We're actually going from the GPU to the CPU. So you just do 2 pandas, and now it's just a regular pandas object. In this case, I wanted to do some stuff that I wasn't really sure how to do in the GPU quickly, and so I was able to just do it using my normal CPU stuff. Of course, pandas is slow. Now it's like, 10x, 100x slower than all the numbers I've shown you before, but you could still do it. So it's nice to have that escape hatch. Same thing with BlazingSQL, you could always do that. But then what I want to show is then for that GPU table of all of our domains, super fast to turn that into the new graph representation that cuGraph wants. And then where it gets really fun is this one where I could try to be very careful with which graph algorithm I want, like, page graph or degree or a core number or connected component analysis, Louvain, or I could just run all of them. And so I found out increasingly for a lot of analysis I do, I just go and I just run all the graph algorithms. And then for every domain or whatever, I just have all of the results. And then once I'm in the visual tool, I could then just kind of play with them and see what they're doing. And that's kind of what the rest of the notebook does, is then we just take the cuGraph object and plot it out. Actually, in the interest of the time, I realize that we're coming up on the clock here. I actually want to jump to the last one. And this one we'll do much more visually. And for the last one, I want to jump to the machine learning side of the RAPIDS ecosystem. So in parallel to a lot of these GPU analytics stuff was the deep learning world. So a lot of people, when you think machine learning, you think maybe exclusively deep learning. And RAPIDS does actually interop there, where you can use RAPIDS to wrangle your data, move it into the deep learning framework, get your, a few enrichment results from the deep learning, and then add that back to your data table for analysis back in RAPIDS. But the reality is, about half the time you want deep learning, half the time you actually want like something like a random forest or other methods. Like if you look at top Kaggle competitions, it's always this kind of toss up, and it really depends on the domain you're working in. If you're doing vision, probably deep learning, but if not, who knows? So what I want to share here is something that we actually end up using a lot, is something called UMAP. And let's switch tabs here. And this is another COVID analysis that we were doing. In this case, we were looking at social media interactions, so communications on Twitter, things like that. This could just as easily been an email analysis, something like that. And I'm actually going to jump straight to the visual, to what's going on to explain this one. So what's going on in this visual is every dot is, let's reload here. As you see, I really like doing live demos for this stuff. Like, one of the fun things about a lot of the GPU computing world is that, like, because things are so fast, we could just do it live. And so in this case, and you can kind of interact live, like, instead of like, waiting minutes or whatever for like your Hadoop or Spark job. Oftentimes, when you get it going smoothly, it's more about like seconds. Okay, so for this one, what I wanted to share is what we're doing with something called Project Domino, where we're looking at COVID misinformation, in particular different accounts on Twitter doing misinformation. And this is kind of a regular setup where you have a bunch of entity, like a machine learning setup, where you have a bunch of entities and you might have a bunch of like features for them. So in this case, we had a bunch of Twitter accounts, and then we were kind of looking at which conspiracy theories they mentioned. So if you're like, let's say in Spark or Splunk or a tool like that, you might have like a bunch of IPs or a bunch of user accounts. And then you might have like a bunch of information like, which country was it in, or how many messages were there. In Twitter, what we care about is like maybe the timestamps they're active, how many friends they have, and in this case, what are the things they're talking about. As soon as we have that table of ones and zeros, or actually, or just numbers in general for each entity, what we run is something called UMAP. And normally UMAP, I always forget what it's called. It's like universal manifold something or other. If you're familiar with TSNE or PCA, just think of it as like 5-10 years after all that stuff. What's cool about UMAP is, by default, with very little work, what you get is something that looks like this. You get, for every entity, you'll kind of get put on screen somewhere, and you can do it to a 2D, 3D, whatever projection. And so just based on the topics, what we're getting is, for each Twitter account, who are they kind of like, which topic, like not only which Twitter accounts are talking about the same conspiracies, it's also sort of like if you think about like an audio wave, like, and you ask like, are two songs like not only singing about the same thing, but actually in the same way, like, they have high bass and low treble, something like that. And so what UMAP is able to do for us is answer, hey, all these accounts, they're both talking about QAnon and chloroquine, or however you pronounce that. But when they're closer together, what that means, they're not only talking about the same thing, but actually in the same intensities. Like, maybe these ones are talking a lot about QAnon, and these ones maybe over here are only talking a little. And actually, maybe they're talking more about this ID 2020. And you can kind of get this not even exact, instead of just exact match, you get a nice fuzzy weighted match. And the distance kind of tells you how far. Then the thing we do after that is you can then take the UMAP, and then we can just draw edges between things that are close. And so now an edge between any two nodes and these two Twitter accounts doesn't mean that they're friends. They may have never mentioned one another, never followed one another. But if there's an edge, that means they sort of are talking about the same thing. And if there's a lot of close and heavy edges, that means they're actually almost like bots doing exactly the same behavior. And so if you're doing something like a bot analysis, this actually ends up being quite interesting. Or let's say you have like an outage and you have like a fleet with like replicated misbehaviors. This would actually kind of start classifying things in the same way. So it ends up being cool. Because it's all living on GPUs, so this is where the interactivity comes in. We have about 100,000 edges on screen. We're actually just clustering them live based off of those inferred connections, and we can play with them. And again, all that data. So in the case of the QAnon stuff, we might want to ask, let's make the ones that talk about QAnon a lot bigger, and then for the QAnon conspiracy, let's also make them hot. Like let's make them pop out a bit more. And so we can kind of see for all the COVID misinformation and conspiracy Twitter, we're seeing QAnon showed up a lot. Like it's all kind of some shade of pink, but then some areas were hotter than others. And behind the scenes where we're doing all the GPU stuff on the server. So anyway, hopefully this has been kind of a fun introduction to Rapids Academy and to the Rapids universe. This has been an experiment. It's the first one we're doing. My hope today was that basically, if you already knew Python, the Python data world, this would feel kind of somewhat familiar, just a little different because of the GPU parts. So I was hoping that, seeing loading in big data sets, doing regex, doing data frames, doing machine learning stuff, all of that should have felt familiar, just and even actually at the level of APIs, and actually, but now you can see that it's quite approachable. If you're already in that world, you actually may have been even seeing to the level that, hey, actually, I already know that exact API. This is I totally get what you did, and then you might be thinking more at the level of like, hey, well, how do I deal with multi-GPU, or how do I deal with multiple nodes of GPU? And you're starting to think more about that stuff. We're actually going to be holding future sessions over the next few months, kind of doing that progression. So I encourage you to join for those. For folks who are hanging on, I encourage you to, I'll close up in a couple minutes, but take a 10-20 minute break. We'll be back at noon Pacific, 3 p.m. Eastern, and then we'll start the lab portion. Again, just head to the rapids.ai Slack, and we'll kind of start splitting folks up into groups for the lab portion and then post instructions there. I'll still be doing the, as we go through that, I'll still be doing the YouTube live stream, so you can kind of see that, just so we won't be recording it. With that, especially for folks who need to, who plan to stay on for the free lab in 20 minutes, I encourage you to take a break. For everyone else, if you want to just hang out, ask questions, looks like we have Winston from the BlazingSQL team. I bet we have some Rapids folks. Actually see Sindre over from the project Domino is with us. So if you have any questions, let me know. I'm gonna stop the recording right now, but I'll be hanging out in the Slack or in the YouTube. Just feel free to ask questions, anything like that. All right, thanks everyone, and appreciate you joining for the first one with us.